Welcome everyone. In this video, I will be covering section 15.8, triple integrals in spherical coordinates. So we saw earlier polar coordinates, how they can be used in evaluating double integrals in an easy way. And we also saw cylindrical coordinates in the previous section, when how it is used to evaluate certain triple integrals, which are hard to evaluate otherwise. Now we are introducing another type of coordinates, which are known as spherical coordinates. And we are going to see in this section how these are applied in evaluating certain triple integrals. The spherical coordinates rho, theta, phi of a point P in space are shown in figure 1, point rho, theta, phi, where rho is the distance between O and P. As shown in this figure, rho is the distance between the point distance from the origin to P. Theta is the same angle as in the cylindrical coordinates or polar coordinates. So theta is the angle between the uh, projection of the point P, which is P prime. So the angle between OP prime and the x-axis on the xy plane, that is theta, which is exactly similar to the angle theta in cylindrical coordinates. The angle between the positive x-axis and the line join of O to the projection P. That is what theta is. And phi is the angle between the positive z-axis and the line segment OP. So we are introducing rho, theta, phi. You already know theta. Rho is spelled as RHO. It's a Greek letter. And then rho, theta, phi are the coordinates of the point P. Rho is as shown in this diagram, which is the distance of the point O to P in space. P is in a point in the space. So from origin to P is a distance, that is rho. What is theta? Take P and project it onto the xy plane. That will be P prime. The angle between the positive x-axis and OP prime is this angle theta. Then the next one is phi. Phi is the angle between the line OP to the positive z-axis. So that is phi. Z-axis and the line segment OP, that is the angle. Now, rho is always positive or 0. Rho is always more than or equal to 0. Phi is the angle between 0 and pi. Theta can be from 0 to 2 pi. The spherical coordinates of the point P are shown in this figure. The spherical coordinate system is usually used in evaluating triple integrals over regions bounded by spheres or cones. The spherical coordinates system is especially useful in problems where there is symmetry about a point. Earlier, we saw cylindrical coordinates were useful when there was symmetry about an axis. Now we will use spherical coordinates in triple integrals where there is symmetry about a point, and the origin is placed at this point. For example, the sphere with center at the origin and radius c has a very simple equation rho equal to c. This is the reason for the name spherical coordinates. Just like cylinder has a very simple equation R equal to C. The cylinder in cylindrical coordinates can be just represented as R equal to C. In spherical coordinates, a sphere can be represented as rho equal to C. The graph of the equation theta equal to C. So look at this graph. So rho equal to C is a sphere which we saw earlier. Theta equal to C is a vertical plane. What is the angle theta in terms of spherical coordinates? Theta is the angle between the positive x-axis and to the line OP prime, where P prime is the projection of the point P onto xy plane. So if phi is a constant, then that represents a half plane. If phi is a constant, theta is a constant, is a half plane. If phi is a constant, then it represents a cone. Phi equal to constant represents, in fact, a half cone with the x-axis, with the z-axis as its axis. So when you say phi equal to constant, that constant can be less, you know that phi lies only between 0 and pi. So if it lies between 0 and pi by 2, then it will be the upper half cone. For phi between 0 and pi by 2. If phi equal to a constant, but that constant lies between pi by 2 and pi, then it will be the lower half cone. Now we'll see this figure and we can get more ideas about x, y, z, converting Cartesian coordinates to spherical coordinates. So here we know that P has a Cartesian coordinates x, y, z, and we are going to convert that to rho theta 5 and how vice versa. So if P is a point in space, then we know that rho, theta, and phi are the spherical coordinates, and rho is the distance between O and P. Theta is the angle between OP prime and the positive x-axis, where P prime is a projection of P onto the xy plane. And then phi is the angle between OP and the positive z-axis. So now let's consider xyz, and we will connect the two variables, connect cylindrical and spherical and Cartesian coordinates. If this angle is phi, then using alternate angle, this angle will also be phi. And you know that this value r is OP prime. Then I can write from this picture the relationship between rectangular and spherical coordinates can be seen from this figure 5. From triangle OPQ and OPP prime, we have Z equal to rho cosine phi. So you have the triangle OPQ. You take the triangle OPQ. From the triangle OPQ, PQ is perpendicular to the z-axis. This is 90 degrees. So rho is the hypotenuse of that triangle. So Z would be or cosine phi for that triangle would be adjacent over hypotenuse, or z equal to rho cosine phi. So we have z equal to rho cosine phi. Then what is r? From the triangle OPP prime, so from the triangle OPP prime, from that triangle, R is a side opposite to phi, and it's a right triangle also. So when you do sine of phi from that triangle, it is opposite over hypotenuse. So it is opposite is r, hypotenuse is rho. So we can say r equal to rho sine phi. So we can write r equal to rho sine phi. Now if you look at the xy plane, where it is xy, where x and y are written, x coordinate and the y coordinate here, and this is the z coordinate of the point. X can be written as r cosine theta, y equal to r sine theta, which we know already. So to convert from spherical to rectangular coordinates, we can use the equations x equal to r cosine theta. But what is r though? R can be written as rho sine phi. So it can be written as rho sine phi in the place of r times cosine theta. Times cosine theta. So x equal to rho sine phi cosine theta. What is y? Y equal to r sine theta. But what is r? R is rho sine phi. So it is rho sine phi sine theta. What is z, which we already mentioned? Rho cosine phi. So in order to convert from spherical to rectangular coordinates, you would use x equal to rho sine phi cosine theta, y equal to rho sine phi sine theta, and z equal to rho cosine phi. You know the meaning of rho, theta, and phi. Rho is a distance between O and P. Theta is the angle between the positive x-axis and OP prime, where P prime is a projection of P onto the xy plane. Phi is the angle between OP and the positive z-axis. Also, the distance formula shows that rho square equal to x square plus y square plus z square. We use this equation in converting from rectangular to spherical coordinates. There are some problems that are done in the videos for the section. Problem number 3 is done in the section video. Then there are more problems done. Number 21 is done in section video. Number 23 is also done in the section video. Please refer to those problems in the videos of the section. Now, how these spherical coordinates are applied um, in triple integrals? How do you change from rectangular coordinates to spherical coordinates in triple integrals? The triple integral over E f of x y z dv is integral c to d, integral alpha to beta, integral g1 of theta phi to g2 of theta phi of f of x, y, z, where x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi, and dv changes to rho square sine phi d rho d theta d phi, where the region of integration E, this rho theta phi, and where rho, we have to give values for each one of these, rho theta phi. So where rho lies between g1 of theta phi to g2 of theta phi. So we will write down the fixed limits first. So because the last value is d phi, so this first integral corresponds to the limits for phi. So phi lies between C and D, and theta lies between alpha and beta. The second integral is for theta, that is this alpha to beta. Then the innermost rho varies from g1 of theta phi to g2 of theta phi. So this is the region of integration. Thus, we replace x by rho sine phi cosine of theta, y by rho sine phi sine of theta, and z by rho cosine phi. Also, we said that this part is the dv part, that is dv by rho square sine phi d rho d theta d phi. In what situations would you change to cylindrical or spherical coordinates? So, what are the scenarios where you would apply cylindrical coordinates, and which of the places would you apply spherical coordinates? We may want to change from rectangular to cylindrical or spherical in a triple integral if the region E of integration is more easily described in cylindrical or spherical coordinates. Regions that involve symmetry about uh, an axis, about the z-axis, are often simpler to describe using cylindrical coordinates. And regions that are symmetric about the origin are often simpler in spherical coordinates. Also, sometimes the integrand is easier to integrate using cylindrical or spherical coordinates. Please make sure to watch the section videos for some of the problems that I mentioned before. Problem number 3, problem number 21, 23. These problems can be verified there. Uh, hope this video helps.